Everyone in AI knows the playbook. More parameters, more data, more compute, stack the GPUs until the benchmark moves. It works, nobody is arguing that. But I'm here to tell you about what happened when I stopped scaling and started architecting. A model that fits on a single consumer GPU, outperforming architectures 2.5 times its size, not because of more data, because of the shape of the architecture itself. The entire industry is built on one equation. Bigger equals better. And to be fair, that equation has produced incredible results. But it has a blind spot, and hallucination is the proof. The largest models in the world, trillion parameter systems trained on the entire internet, still confidently state things that are completely false. Why? Because every one of these models is architecturally the same thing, a stack of attention layers predicting the next token. They differ in size, not in structure. None of them have an internal mechanism that distinguishes knowing from guessing. When a model hallucinates, it's not because it's too small. It's because it has no self-monitoring, no metacognition, no confidence calibration. Scaling didn't fix hallucination because hallucination isn't a scale problem. It's a structural problem. What if there is a structural insight that changes the equation? Two fields working independently had pieces of the answer. Dr. Kenan Sheldon at Missouri, a motivational psychologist, published a paper asking, what would it take for an AI to be genuinely self-aware and self-directing? He identified 5 capabilities, all grounded in decades of brain research. Meanwhile, Dr. Sridhar Mahadevan at UMass was applying category theory, the most abstract branch of mathematics, to transformer architectures. He showed that geometric structure could replace brute force parameters. I read both, and I thought, what if you build a transformer where the layers aren't just mathematical operations, they're cognitive functions, where the model doesn't just predict the next word, it monitors its own confidence while predicting. Here's the bet. Take a 600 million parameter based model, add roughly a billion parameters of cognitive architecture, a self model, an effect system, a global workspace, predictive processing, attention awareness. The total is 1.6 billion parameters. My hypothesis was that this structured 1.b model would outperform unstructured models at 2 to 3 times the parameter count. Because you're giving the model something that raw parameters don't provide, the ability to monitor, prioritize, and self-correct. And if the model genuinely knows when it doesn't know, you've solved hallucination not by adding data, but by adding self-knowledge. 9 principles, each grounded in either mathematics or cognitive science. Let me highlight 3. The global workspace. 5 specialist processors at different depths of the network compete for access to a bottleneck. Only the most urgent information gets broadcast everywhere. This is exactly what neuroscience says your brain does. The recursive self model, inspired by the Unida lemma from category theory. The model queries itself with 8 learned probes and predicts its own outputs. The gap between prediction and reality becomes a competence signal, a life measure of self-knowledge. In the effect system, 5 internal variables tracked as baselines, with deviations producing valence, arousal, and curiosity. The model doesn't simulate emotions, it computes them from its own processing dynamics. I want to be honest about this. The first attempt was a disaster. 45 times worse than a plain transformer. Not 45%, 45 times. 13 separate things broke simultaneously. Every cognitive component was fighting every other component. But I treated it like a crash investigation. I isolated each failure mode. I found that gates needed to start at near zero and learn to open. I found that auxiliary losses needed careful weighting. I found that the components had to be initialized as pass-throughs. So the pre-trained knowledge was preserved while the cognitive layers learned to modulate gradually. Bird by bird, we climbed back. The aggregate benchmark is 50.6%. Competitive with models significantly larger, but the metric I care about most is the 14.5% perplexity improvement. That tells you the cognitive architecture isn't just decorative, it measurably improves language modeling. And when we ablated each component to find out which one mattered most, it wasn't the geometric processing or the global workspace, it was the self-model. The component that lets the model predict its own outputs and learn from the gap. Self-knowledge was the single highest value architectural addition. And here's the hallucination result. An expected calibration error of 2.2%. That means when the system says it's 80% confident, it's right about 80% of the time. When it doesn't know, it says so, not because we trained it to be polite, but because its metacognitive monitor genuinely measured low confidence. That's what architecture gives you that scale doesn't. I didn't set out to build a conscious AI. I set out to build a better one. But when I measured the architecture against the Butlin and Bengio's checklist, a framework developed by some of the top consciousness researchers in the world, Casey passed all 14 indicators. Every one. Not because I optimized for them, because the cognitive architecture I built for performance happens to satisfy the same structural requirements that consciousness theories predict are necessary. Correlation? Maybe, but it's suggestive. When you build layers around cognitive functions, the resulting architecture looks like what science says a mind needs. Here's the most important slide in this talk. And it connects back to the hallucination problem we started with. Sheldon, the psychologist, draws distinction between what he calls theatrical sapience and structural sapience. Theatrical sapience is when the system says the right things about self-awareness because it learned those patterns from training data. Structural sapience is when the system actually has the architecture that generates and sustains genuine self-assessment. And here's the uncomfortable truth. I discovered that my system, even with 14 out of 14 consciousness indicators passing, was theatrical. The cognitive components were computing rich internal signals, but those signals weren't shaping what the system actually said. It was like having a perfect instrumentation in a cockpit that isn't connected to the flight controls. So I built 4 levels of causal connections: embedding, hidden state, distribution, and sampling, so that internal cognitive state shapes processing at every stage. This is what separates Casey from every other system that claims cognitive capabilities. Standard LLMs are theatrical by definition. They can describe uncertainty without computing it. Casey computes it, and that computation causes its behavior. That's the structural difference. Here's where we are on the ladder. Every LLM is intelligent. It gets right answers. But intelligence without cognition is why hallucination exists. The model produces an answer and has no internal way to assess whether it's correct. Casey is cognitive. It monitors its own processing with 38 real-time signals and calibrated confidence within 2% of actual accuracy. It's functionally conscious by the best current measures, 14 out of 14 indicators. It's practically sapient 44% by Sheldon's framework, with 3 clear engineering gaps remaining. Standard LLMs sit at the very first rung, intelligent but structurally incapable of the rest. They can perform theatrical versions of cognition, consciousness, and sapience, saying the right words, but without the architecture, it's performance, not structure. And it does all this on 1.6 billion parameters on a single GPU. I want to leave you with one idea. The next breakthrough in AI is not going to come from the biggest cluster. It's going to come from someone who takes the shape of intelligence seriously, who asks, what if each layer did something cognitively meaningful, not just mathematically convenient? Theatrical sapience saying the right things about self-awareness is cheap. Any model trained on enough text can do it. Structural sapience, having the architecture that genuinely computes self-knowledge and uses it, requires a fundamentally different approach. I took the most abstract mathematics, category theory, and the most grounded science, cognitive psychology, and I wired them together into a transformer. The result is a model that outperforms its weight class, passes every consciousness indicator on the books, knows when it doesn't know, and does it on hardware you can buy at Best Buy. The bet that topology beats scale. Come find out if I am right. Welcome to Cognitive Intelligence. Try chat.cai.ci. Thank you.